Everybody, my name is Taylor Sparks. I'm the editor-in-chief at Integrating Materials and Manufacturing Innovation, IMMI. And I'm here to talk about this paper, which is about the assessment of hot cracking susceptibility through interdendritic feeding simulations. This work comes to us from Maile, Oriola, Giblin, Nguyen, and Payton, all in the Department of Mechanical and Materials Engineering at the University of Cincinnati. Now, they're talking about hot cracking. So what is that? Hot cracking is when alloys crack, particularly during welding, casting, or 3D printing, and it is unfortunately a very common occurrence. Now, hot cracking has been around for a while, and it is complex and hard to understand. It's actually a fairly complex phenomenon going on. And so, unsurprisingly, a lot of people have dug into this. For example, this work by Tsao and Co. on hot cracking of binary magnesium aluminum alloy castings, or this review of existing solidification crack tests and their analysis by Wall and Benoit, and most importantly, the recent paper by Giorgio and co-workers on a new approach for modeling it. They point out that this present work tries to focus on the interdendritic region and the flow of liquid into those spaces where shrinkage is occurring. And this is really best shown with a diagram. This diagram does a good job of showing it. Metals typically shrink upon cooling as they solidify, typically something like 2 to 6%. And so you have these solidified regions shown in light gray here growing in dendrites outward, and we're relying on the liquid metal flowing into these interdendritic regions to backfill the space during solidification. And if it's not able to do that, if it's not able to flow quickly enough, for example, then as it shrinks, we're going to be left with these voids. And if those voids link together, they become cracks, and that is the root of this problem. Now, modeling these has been a challenge traditionally, but one of the more interesting approaches that's come out only since 2021 is this Giorgio's model, which uses the shield profile to assume the interdendritic funnel wall, and then this is mirrored, and the resulting geometry is used as an approximation for your interdendritic regime, right? It's not perfect, but that's an approximation. This funnel-like geometry is used for laminar flow simulations, and from that you can actually back calculate the pressure differential between the entrance and the exit, which then they use to assess whether or not something is going to crack. So what's different in this work? In this updated model, it says they're going to maintain the benefit of only needing CalFAD to calculate these as inputs, but it's going to be altered by utilizing a calculated phase differential made possible through the solidification shrinkage values and allowing the model to solve for the velocity differential. In other words, they're really asking, can we do better by directly modeling how fast the liquid flows instead of just the pressure drop, and by including alloy shrinkage as a driving force for this? So when you get into the methodology, the great thing about this is that it only needs CalFAD and COMSOL, and they're able to do a bunch of different simulations under different conditions. For example, they're able to calculate the pressure differential for many different alloys as a function of normalization factor, as outlet width, and their key finding is shown in this figure 15, where they're showing now a comparison of the Coe and the Klein methods for against the unmodified and the modified FRT method for utilizing pressure and flow velocity as a predictor of crack susceptibility for both refractory high entropy alloys as well as steels. And basically what they show is that there's not one model that works perfectly for everything. They show that the FRT model tends to do better on steels, but this modified FRT one tends to do a bit better on the refractory high entropy alloys. So what's the bottom line here? There isn't yet a one-size-fits-all model for predicting cracking, hot cracking, unfortunately. But this does give evidence to the notion that incorporating the physics behind our simulations to tweak our models, accounting for example, solidification shrinkage, could help us better predict when and how cracks are going to form in a material. So check it out yourself in the latest issue of IMMI.